All right, howdy everybody. So today I'm going to be talking about Faulds, which is an iterative classifier that we created to do internet-wide OS fingerprinting. So let me give you an agenda of our talk. I'll introduce the problem. I'll go over a few of OS fingerprinting techniques, and then dive into iterative classification. Round it all off with an internet scan, and then conclude. All right? So the internet today is just exploding with all kinds of devices, right? You have phones, printers, IoT, medical devices, everything's coming online. And this really builds a unique attack vector for hackers, but also provides some interesting measurement opportunities for researchers. One technique to discover these devices is OS fingerprinting, right? It determines the OS of a remote host, but can also fingerprint specific firmware. So we can find these devices like printers and webcams. So this technique is widely used in network security. Attackers use this as part of their recon phase for discovering a network. Administrators use this to survey their own networks, find vulnerable hosts. IDS actually uses this to find out what OSs they're actually protecting so they can protect them better. And then used by researchers and market analysts to measure networks. So our focus in this work is improving the results of large-scale OS fingerprinting, which has recently come to the fore. We want to extract as much information as we can, and also don't want to increase our measurement footprint. So to give you a little bit of background on fingerprinting methods, for this talk, we focus on active fingerprinting. Passive methods like POF, they require access to traffic, to existing traffic between the target and the scanner, which, on a large scale, as we want to do, this can be difficult unless you have access to a major internet backbone. So we focus on active methods that actually send out probes to the target and get responses back that we can use to fingerprint. So this category breaks up into three types. The first is banner grabbing. To do this on large scale, you have to know the protocol because you're grabbing the banner from an HTTP or FTP or telnet connection. And these days, this is defeated by generic software. Like you have Apache, Nginx, which run on multi-platform. And if you see that string, you don't know what the underlying OS is. And of course, administrators can just go in and scrub these strings out. Multi-probe tools, the most popular one, Nmap, and then Xprobe, as well as some clock skew methods. Whoops. All right. So using these on large scale is a problem, right? If you try to Nmap the internet like I did, well, prepare your inbox because you're going to get a lot of complaints. They generally send malformed packets, so you can potentially crash the target host, which is not what you want to do. And it's too slow for millions of targets, as well as packets are usually dropped by any IDS system. So we're going to focus on single probe methods. And these four have been introduced in the past few years. And I'm going to go over how they work next. So single probe techniques usually rely on TCP probes, and they use two features for classification. Broken down into network features, which can be modified by network effects, and user features, which can be modified by the end user. So an example signature looks kind of like this. We have our Windows 7 signature here. We extract certain features from the IP and TCP headers, so like window size, TTL, options, maximum segment size, which makes up the user features. And then we look at the SYNAC retransmission timeouts, which make up the network features. So here for Windows 7, its RTO vector looks like 3 seconds, 6 seconds, and 12 seconds. And I'll explain what that means in a bit. But the point here that I want to make is, if you look at our three examples here, they can vary a lot. So the user features are quite different between these three OSs. and the RTO vectors are also quite different. So as I said, the network features are SYNAC RTOs, and the way they work is this. So imagine our client is our scanner, the server is the target. We send a single SYN probe. Now that SYN probe has attached to it a forward delay. And when it gets to the target, there's a bit of server think time before the SYNAC is generated back. So we captured that delay, those two delays, as this variable t. Now the SYNAC, on the way back, has its own one-way delay back to us. We captured that in delta. R1, R2, R3 here are the observed RTOs on the scanner. And we take our Windows example here that sent SYNACs after 3 seconds, 6 seconds, and 12 seconds. But of course, if you're doing a measurement on the internet, you're not going to see 3, 6, 12 back. There's going to be delays. So say we have large delay in that first packet, we might see something like 2.8, 6.4, 12.1. And not only delays, we also have loss, right? So you can lose a packet. Now you see 9.2, 12.1. You lose the other one, you see 2.8, 18.5. As you can see, these are going far away from the original 3, 6, 12. You can lose 2 packets and you only see one RTO of 21.3. So there's a lot of possibilities here. I won't go through all of them. But the point is the classifier has to be able to figure out what it's actually looking at and what could have happened. Now the user features, these can be typically modified in the Windows registry or Linux file settings. And these usually result in arbitrary fluctuations, right? A user will most likely go and change an 8K window size to 65K, not 8K plus 1. Sorry about that. So really what we have to do is treat all our features as volatile. So an observed sample can have many matches, right? So if we observe this yellow row here, well, was it a Windows user that went and upped his window size, dropped a couple options, and we saw packet loss? Or is it an HP printer for which the TTL is lowered, a couple options are dropped, and then we lost 3 packets there? So again, the classifier has to make these decisions as it goes along. So the most recent classifier to do this is Herschel Plus, which came out last year. I'm just going to briefly review how it works because it lays the foundation for our work. So let D be a database of known OSs. Each OS omega I has its own feature vector or fingerprint. And suppose Y is a random observation from some target. So then what Herschel Plus does is it determines the most probable omega I that could have produced it given the observation Y. Plugged in tight enough. All right, and this also depends on the prior probability of that OS, as well as theta, which describes the noise model which I talked about. So it includes T, our delta, packet loss, as well as user tweaking, all in that theta there. So Herschel Plus then builds this complex model which relies on prior knowledge of alpha and theta. Now for the internet, that's hard to come by, so it makes several assumptions, right? It says, well, we treat alpha as uniform, we treat forward delay T as a summation of 2 exponential distributions, so we get a fixed Erlang. One-way delay is treated as a fixed exponential. Packet loss is fixed at 3.8%, which is from a Google study in the past. And each user feature has a probability, fixed probability pi to be tweaked. So of course, there's issues with these static assumptions. They don't really allow flexibility in the network that we're studying. So alpha is most certainly not going to be uniform in practice. Each OS is not equally likely on the internet. Network conditions can change drastically, and user feature modifications generally vary per device. So a user is more likely to change a Windows host than to hack their printer. Well, so the goal of our work is to solve these problems and actually recover this true alpha and theta. So moving on to iterative classification. So as I said, the performance of Herschel Plus depends on how well you can estimate that alpha and theta beforehand. And evolving networks make this really difficult. We argue that alpha theta should be the output of the classifier and not the input. So to do this, we develop an iterative classifier called Faulds that actually produces this output as part of its classification. And as an aside here, we name our method after Dr. Henry Faulds, who was a Scottish scientist who actually did the first scientific study of human fingerprints back in 1880. So we derive several update equations for each parameter in alpha theta to iteratively build this output. We also prove that our update equations actually fall into the expectation maximization framework, so we get those nice convergence properties. So for example, here's our result for updating alpha. So way to read this is alpha at iteration t plus 1 is the average probability of all observations matching to OS omega I. And we expand out this probability in closed form for the Herschel Plus classifier. So this is not as trivial as it seems. And of course, this is conditioned on previous estimates of theta and alpha. So we follow similar methodology for building distributions for all our distributions in the theta noise model. Don't have time to go through all that notation and derivations here today, so please see the update paper for all our update formulas and derivations. But really what this allows us to do is to customize folds to the network that we're studying. So some networks may contain larger delays or loss, like wireless, and it also allows us to build a device-specific OS user feature models. So this allows us to see how often users are actually going in and changing those user features. So before we take this out on the internet, we want to test this in several simulations. So our plan is to expose this to various scenarios, see how it does, before using it out in the wild. So we find 3 signatures in the Herschel Plus database, which contains 420 stacks. And we simulate 2 to the 18 samples with different alpha theta. So our database that we pick is this. We pick a Linux, a Windows, and a Novell signature. And we try to pick them so there are differences here in the window size, but there are similarities in some of the other user features. And RTOs here, as you can see for Linux and Windows, are fairly close. So we can potentially introduce some confusion there for our test. So first, we look at simulating different network conditions. So in our first scenario, we set the real alpha to be 90% Linux, 5% Windows, and 5% Novell. And the network parameters follow assumptions of Herschel Plus. So as you can see on this test, Herschel Plus gets a 67% accuracy. And the recovered alphas are tending towards correctness. It's going to 60% Linux. And you can see it's kind of trying to get there, but that's what Faulds actually does, is it goes on, iterates over it, and recovers very close to the correct alpha, and that helps us get 95% accuracy. Now in our second scenario, we change our network parameters to Pareto, and we also test non-uniform packet loss. So we say if your vector has 3 packets, we drop with 10%. If it has 4 packets, we drop 2/3 of them. So here, this causes problems for Herschel Plus. it goes down to 45%. The recovered alpha are getting further away. But Faulds actually is able to recover the correct alpha, FT, F delta, and packet loss to get a pretty perfect alpha as well as 97% accuracy. So the next thing we look at is user features. So in this scenario, we change our alpha to 70, 20, and 10%. And we say, okay, in this network, there were a bunch of OS patches deployed that went and changed the user features of each OS to another fixed value with 80% probability. And this causes problems for Herschel Plus because it does not know what those new values are. So its accuracy lowers down to 31%, and the alphas are also wrong. Whereas Faulds, interestingly, learns what those new values of those OSs are for those features, and actually is able to recover 100%. And then finally, we say, okay, now we have a bunch of tricky users in our network that actually are scrubbing these user features non-uniformly. So they always change the window size, the TTL, and the MSS, and the DF and options are not changed all the time, but with pretty high probability as well. And this really tanks Herschel Plus. It's completely tricked. The accuracy goes down even further, whereas Faulds learns those true pi vectors and is able to recover that as well. So there's more scenarios in the paper. So please, I encourage you to go look at those. So besides our little toy database, we also test Faulds on the full Herschel Plus database. And what we try to do is simulate some counterintuitive examples. So setting F delta to be a reverse exponential distribution. So it looks like this. You can see the solid line. That's the real delay. And as you can see, our initial guess for that delay is nowhere close. But interestingly, by iteration 1, it's already kind of forming to be closer to that. By iteration 10, it's almost there. And when it's converged at iteration 100, you can see it fairly accurately recovers that weird custom delay that we came up with. And this really impressed us and showed us Faulds can recover these complex distributions. And we were ready to take it out on the internet. So we did a SYN scan of all BGP reachable IP, IPv4 on port 80. So we're hitting web servers. About 3 billion IPs received 67 million responses. And then we unleashed Faulds on this data set for 100 iterations using the full Herschel Plus database. So this is our recovered empirical FT and F delta, which seems pretty reasonable. As you can see, there's a spike in FT at 60, which we are guessing are US-based destinations. And then other spikes here correspond to overseas as well as busy servers. And then F delta spikes at around 10 to 12 milliseconds with an average of 15, which is pretty reasonable for random queuing delay. Now, during classification, Faulds actually consolidates several signatures because it learns how certain signatures can be tweaked by users. So what actually happens is if we look at the top 10 classified OSs, in iteration 1, we have a mix of Linux here on the top, a sprinkle of Windows here, and some embedded devices as well. But by iteration 100, it's consolidated some of those Linux signatures into the top Ubuntu signature here because it learns that, oh, I can also see different window sizes for this same signature. And it actually allows other signatures to sneak into the top 10. So like this Dell Laser and Cisco Embedded that were not in the top 10 before start showing up. Now, as I said, Faulds also helps us study how end users modify these devices. Right? So our Ubuntu signature here, we saw a couple different window sizes, 28,960 being the most popular, and then half of that 14,480 as well. at 31%. And we see a couple other window sizes. But interestingly, our MSS, for 98% of hosts, we see only 1460, which leads us to believe we saw most of these Linux servers, web servers out there that are on enterprise networks or cloud networks that have a pretty stable 1460 connection. Now, realize that MSS does also depend on the underlying link layer that you are connecting with. So if we look at another OS, here Mac OS, we see a lot of different window sizes. So 65K being the default and the most popular, but we also see some tweaking to lower window sizes. And we also see a lot of different MSS values. So this corresponds to users perhaps connecting from different types of connections, your DSLs, point-to-point, which actually adds more to the packet. And then we look at our printers. For 99.9% of them, and we had 900 million signatures for these Dell printers, 900 million matches, almost all of them have the same window size. So this really shows us no one's really going in and hacking their printers that much to change the window size. We do see 3 different MSS values, though. Now, we also saw some interesting devices from our scan. So we see a lot of video conferencing devices, some IP phones, some lighting control systems, which pose interesting security questions for why they're available over the public internet. And remember, we are scanning for web servers here, so these are most likely the configuration panels for these devices. Most likely, if you scan for different ports, you can find even more of these. And then finally, we also see a large number of old OSs. So this was brought to the fore with recent ransomware, WannaCry, which infected Windows XP in 2000. But we still see 1.5 million of those machines out there, as well as several old Windows servers, some old FreeBSD, Solaris, and Mac OS. So, it's interesting to see that these are still running web servers out there. So to conclude, we introduced an iterative EM-based classifier called Faulds to improve single-probe fingerprinting. We showed it outperforms the previous best, Herschel Plus. And we also were able to build a much more detailed output without increasing the measurement cost, because we're still staying with that single probe. And then finally, using an internet scan, we use Faulds to produce interesting OS measurements from across the world. And that's it. Thank you for your attention.
Hi, Nick Nikiforakis, Stony Brook. Thank you for your work. So, did you look at all? I understand that during your internet scan, you sent sort of SYN packets to every IP address in the V4 space. Did you try to see if you would try to do this based on a domain name, where you resolve the domain and then you scan it, right? How would these very large-scale reverse proxies like Cloudflare and other DDoS providers, how they would mask the original identity of an end host? Did you look at this at all?
Do you mean you'd be able to get ground truth from those?
Right, because let's say we resolve Facebook.com and they're protected by some sort of reverse proxy. You connect to that reverse proxy, so you start fingerprinting that reverse proxy.
Yes, so yeah, we're only sending a single probe, and we always hit the forward-facing whatever it is, right? We could be hitting a load balancer, a proxy, so we don't have access to send that probe further down the line. So we are fingerprinting that original.
Right. So I understand that you can your method works when you want to do this census of the internet. But if I want to sort of say, okay, what are you running? I would in fact be hitting what it is that that their load balancers are running, or what it is that their CDNs are running.
Yeah, we can only see the front-facing device. That's right.
Right. And so could you also, maybe you mentioned this, but could you comment how fast this process is for you? In order to do the 100 iterations against a single host, how long would it take for Faulds to run and to do the classification?
Well, our code was running at around 3,500 hosts per second. This was on 68 million internet scan sample. So it took us about 5 to 6 hours per iteration.
Okay, so it should be negligible against one host.
Yeah.
Okay. Is this open source, or will you open source it?
Yes.
Okay, thank you.
Thank you for the talk. My name is Hung from National University of Singapore. It might be out of scope, but can you just comment on, is it, I understand that by allowing the delta and the alpha and the delta to be updated, you get more accurate fingerprinting later on. But could it be updated in a malicious way so that they screw up the entire thing? I mean, it might be out of scope. Like some user might be just malicious and playing around with the tool, and then they tweak their alpha, or a group of users tweak their alpha and delta so much that it would lead to the wrong version later on. And by having the wrong alpha and delta, it could damage the entire accuracy of everything. It might be out of scope, but I'm just curious.
I get what you're saying. So, but we're building alpha theta off a huge internet scan, right? So it depends on how many hosts you control to be able to do that. If you can control a large part of the network, then Faulds will actually learn those are the new values for that OS. So that's what it'll classify.
Right. Thank you.
Hi, Ben Stock from CISPA. A very interesting talk. I was wondering, for the internet-wide scans, you don't really have a ground truth, but did you have a look at, for example, server signatures in the sense of like the X powered by header, where you sometimes have like the PHP version dash Ubuntu, so you know for a fact that, well, assuming there's no reverse proxy, but the web server is actually running Ubuntu. Did you actually check whether your results would correlate with kind of this sparse information that you might get about the server?
So we did look into that. We tried to look into whether we can actually compare to results from either Shodan or Census, because those actually grab the banner. We didn't actually find a scan on the same day, so it's not always correlated. But yeah, that's certainly something we're looking into for the future.
All right, yeah, thanks.
Yeah.
Let's thank the speaker again, and that's the end of the network security session. Here.